Hi, I'm Omnik, and after all those at Coder supposedly beginner contests, I need a win, so I'm gonna do third division at first round, and hopefully I can solve everything. Uh, it would be very embarrassing if I won't be able to solve all the problems. Well, problem A, lever. In Divergent Universe, the lever iterates itself given to arrays A and B of length n. In each iteration, the lever will do the following. Choose a random index I such that AI is greater than bi, then decrease AI by 1. If there does not exist such, I ignore this step. Choose random index I such that AI is smaller than bi and then increase by 1. After each iteration, the lever will check if step 1 is ignored, and if so, it will end its iteration. So, only if step 1 is ignored. But if step 2 is ignored, it will continue. You are given two arrays, find the number of iterations that the lever does. It can be shown that this number is fixed over all possibilities of random indices that the lever can choose for each step. Well, yeah, because the number of times step 1 will happen is just sum of AI minus BI over all positions where it is greater, and the number of times step 2 will happen is sum of BI minus AI over all the positions where AI is smaller. So we need to calculate those values. Why is the limitation so small? You can just write what is written here. Okay, whatever. I guess it's third division contest. Yeah, we need to calculate the number of times first step can happen, the number of times second step will happen. If those numbers A and B, then after A plus 1 iterations, it will stop for sure. But before A plus 1 steps, it cannot stop. So, second sync is not needed at all. I mean, yeah, the end condition only depends on whether step 1 is ignored. So the answer is just sum of like maximum of 0 and AI minus BI plus 1. Okay. It's crazy that the limitations are so small, but also we will have 10,000 tests. Like, I guess you still can implement it like in a stupid way, just like what's written in the statement. It will be like the maximum number of iterations is n times maximum of AI minus minimum of BI plus 1. So it's like 91. And even if you do every iteration in linear time, it's still like n squared times maximum number, and it is fine for 10,000 tests. But like, what is the point? Yeah. I'm assuming we are given like AIs first and then BI. If we were given like A1, B1, A2, B2, A3, B3, we would not have to store the array. How many problems are there? 8? What is this? Long ago, there were like 5 problems in a round, so in Div.2 and Div.1 together there were just 7 problems. And now there is 8 in third division contest. Okay, sure. Problem B, alternating series. You are given an integer n, call an array A of length n good if for all I from 1 to n non-inclusive, the product is smaller than 0. So the 2 consecutive elements must be of different signs. And we can't have any zeros if n is at least 2, and it is. So the elements must have like alternating signs. Okay. For all subarrays with length at least 2, the sum of all elements in the subarray is positive. Okay. Additionally, we say a good array A of length n is better than another good array B of length n if the sequence of absolute values is lexicographically smaller than the sequence of absolute values of B. And that's like problem B of third division contest. There's just so many things to remember already. Output a good array of length n such that it is better than every other good array of length n. Okay, so this is just like print lex mean answer if we consider lex mean after taking absolute values. Okay, then it's not that bad. I mean, still, it's a lot to remember for problem B. Okay, for all subarrays with length at least 2, the sum of all elements is positive. So we can't have zeros, so our elements must be at least 1 by absolute value. Can we have just ones? Well, not exactly. If the length of array is at least 4, then we will have at least 2 negative elements, and we can have subarray with endpoints in those negative elements. So, okay, yes, I need to draw stuff. So my array will look something like plus a1 minus a2 plus a3 minus a4 and so on, because the signs must alternate. Because the product of 2 consecutive elements less than 0, it means that one of them is positive and the other one is negative. Right, so I can look at this subarray of length 3 that has like negative, positive, and the negative element. And the sum of this subarray must be positive, so minus a2 plus a3 minus a4. must be strictly greater than 0, so A3 must be strictly greater than A2 plus A4. But also, it should be pretty obvious that all the negative elements must be -1s, right? Like, it doesn't make sense to make them um, more negative, like but bigger by absolute value but negative, uh, because, well, we want like geographically minimum, so we want to minimize absolute values of elements, like if possible, um, but then like for positive elements, they like we might have to make them bigger than just one, because we have this limitation that sums on subsegments must be positive. But for negative elements, making them like smaller in absolute value is always good. Uh, it cannot like make any subsegment worse because it increases the value even though the absolute value decreases. So all the negative elements are actually ones, like, or -1s, I mean. So the negative elements are -1s, and so this is actually like 1 plus 1 equal to 2. So A3 must be at least 3, but still, but we want it to be as small as possible, so it will be 3. What about A1? Oh, no, I cannot say that yet. Like, A3 must be at least 3, but maybe it has to be bigger. Well, let's show that like the property we are working with is that sum on every segment of length at least 2 is positive. I want to prove that it doesn't make sense to check it for long segments. Let's say we have a segment of length at least 4. Then we can split it in half. The halves may be of different lengths, but we will try to like make it as even as possible. Or actually, we just need to make sure that both halves have length at least 2. Then, like, both halves also must have positive sum because they have length at least 2. So if both halves have positive sum and they're non-overlapping, then the union of those segments also have positive sum because like sum of two positive numbers is positive. So if we make sure that that property is true for every segment of lengths 2 and 3, then we don't have to check it for bigger lengths because every segment of bigger lengths can be split into 2 segments of smaller lengths for which the sum is already positive, so we're good. So we only need to check segments of lengths 2 and 3, and well, it should be pretty clear that basically if we have a positive element that is between 2 negative ones, then it must be at least 3, because we can take a segment like this and our negative elements are -1, so for this segment to have a positive sum, this element must be 3 or more. But for positive elements that are on the border, that do not have 2 negative neighbors, they can be just 2, because like we need to make this segment of length 2 to have positive sum, so it cannot be 1, but 2 is enough. So if we start with a positive number, then our array will be like 2 minus 1, then 3 minus 1, 3 minus 1, and so on. maybe maybe it just ends on -1, or maybe there is a 2 in the end. But if we start with a negative element, we will have -1 at the start and then 3 right away. But it is better because we're comparing arrays lexicographically, and even though like the first positive number is bigger, it is more important to make the first overall number to be smaller by absolute value. So we want to make it 1, but that can be done only if we start with a negative value. So our array will actually look like this. And then in the end there might be a 2 if the length is even, and if it is odd then it's just -1 3 -1 3, and it will end on -1. You would need some special handling for n equal to 1, because we might not have negative elements at all, but n is at least 2, so it just works. But you like, it is a good habit to check for small n, because like we usually imagine like general case. So like I drew here, like we have a lot of elements, so there is an element with 2 negative neighbors, but like that might not be true. For n equal to 2, there will be just 1 positive and 1 negative element. We don't have segments of length 3 at all, but it turns out that it doesn't matter in this case. Like the general solution will still be correct. So our array is mostly like alternated -1 and 3. And then if n was odd, then I printed n-1 elements, and I need to end with another -1. But if n was even, I printed n-2 elements. The next one should be -1, but then the next one is 2 instead of 3. Problem C, make it equal. Given two multisets S and T of size n and the positive integer k, you may perform the following operations any number including 0 of times on S. So we are making operations only on S, and in the end we want to make S equal to T. Okay. So our operation is select an element x in S and remove one occurrence of x in S from S. Then either insert x plus k into S or insert the absolute value of x minus k into S. So basically we can take an element and either add k or subtract k, but if it becomes negative we take absolute value. Okay, and we can do any number of operations. Sure, so basically we can take an element and move it as long as we want. So like if there wasn't this modulo sign, then every element would just stay the same modulo k, but we could get anything modulo, like any number with the same remainder modulo k. But because of this absolute value, like it's a bit different, but we can imagine it as the number will stay like negative, will do not take absolute value. So we can imagine it like on a number line, and we can move it like by k to the right or by k to the left. But if it goes like to the left of 0, we kind of must like make it like symmetry from 0. But instead we can, I don't know, you can imagine like bending the number line on itself, and like we still move by k in any direction. So like we can get to negative values, and then from there we can continue moving to the negative values. But like the actual value is like the absolute value, and like when we continue like decreasing the number when we're already negative, like the actual operation will be plus k, but like it's still allowed. So like we can imagine that we're moving on this like banded number line, and actually like it just means that we can have like our original remainder modulo k, or we can try to go to the negative and get like maybe some other remainder modulo k. It will be like basically minus x modulo k, and from there we can choose any non-negative number with that remainder. So basically we don't have just one fixed remainder, we can choose between two, like x and minus x modulo k. And now we need to check if s and t like can be made the same. So basically just count the number of times like each like element up to the operation we allowed. So like we split the remainders into pairs, and like the remainders that are in pairs are actually counted as the same. Then we count the number of elements with like of that class, and those numbers must be the same for s and t for the answer to be yes. Otherwise it's no. So like to implement that, basically we will find like the minimum number we can make one, and it's like kind of a general approach. If we have some kind of operation, we can see that it can be like undone. We can always undo the operation. So our operations basically like build a graph on the like possible states, and we want to basically find connected components. And from every connected component, you can choose like a representative for that component, which is basically like we choosing one element in the component and saying, okay, so all the other elements in this component are equivalent to that one. And usually it's useful to choose like extreme element in some way, like minimal in some way, and then like you can just replace every element by its representative. Okay, so in this problem I don't need to well, I will have a map, so I guess I'm storing the array. So I read the element, now I want to find its representative, the smallest number that I can transform it to. So it would be just x modulo k if we didn't bend the line, but now that we bend the line, x is minimum from x and k minus x. And now I'm doing the same for array B, but doing minus minus in the map. And now I need to check that all the values start in map as zeros. Okay. Why did I use map and not unordered map? Because for map I know the complexity and it's always the same. I can be sure that every operation I do works in logarithmic time, and like it might be not fast, but I know that it is not possible to break it. For an ordered map, like yeah, it's like constant on average and like normally it's fine, but like you can build anti-hash tests when like an ordered map will blow up the complexity and become like linear in every operation. And also built-in C++ unordered map is not that fast, like it has bad constant factor. So for simple cases, like if the time is not an issue, I prefer solution that is slower, but I can be sure that it's like that slow but not worse in any situation. If you just write unordered map, like be prepared to get time limit. Because there are bad tests, and in this particular problem it is very easy to construct a bad test because like the numbers are just given in input. Problem D, something in Latin. Arboris contractio. Or maybe not in Latin, I don't know. Maybe it's just some Roman language. Kagari is preparing to archive a tree and she knows the cost of doing so will depend on its diameter. To keep the expense down, her goal is to shrink the diameter as much as possible first. She can perform the following operation on the tree. Choose two vertices S and T, let the sequence of vertices on the simple path from S to T be this. Remove all edges along the path, in other words, remove edges along the path. Connect vertices V1, V2, so on Vk directly to V0. In other words, at edges V0, V1, V0, V2, and so on. It can be shown that the graph is still a tree after the operation. Sure. Help her determine the minimum number of operations required to achieve the minimal diameter. Well, I'm pretty sure that you can achieve a star graph. Just choose one vertex and like apply the operation like from that vertex to any other vertex that is not directly connected. It will become directly connected. So like after some number of iterations we can get a star. And the star obviously has the minimal diameter. So and like it's the only way to achieve diameter too. So we want to get a star. But is it like, is it the best we can do? Like choose some vertex and then just apply the operation to all the leaves, like well, basically root by that vertex, and take all the leaves that are not directly connected to that vertex, and like that's the answer. We can always achieve that. Can we do better? I would guess no, but I wouldn't say it's obvious. It's probably true. Something like there will be a vertex V that will be like the center of the star in the end. Like we can choose it beforehand. And let's look at all the leaves that are not directly connected to that vertex V. I want to state that no operation can reduce more than one, like reduce that set by more than one vertex. So make two different leaves to be directly connected to V. The only way to change anything, like increase the connections of V to any vertices, to choose V as start of the path, and then for every vertex that is not on the path, it will not be connected to V if it wasn't before, and on the path there is at most one vertex that was a leaf before that, like the other end of the path, because for the vertices that are not the ends of the path, they're certainly not leaves because they have at least two neighbors. So for given vertex V that will be the center of the star, the number of iterations is at least the number of leaves in the tree that are not directly connected to V. And we can achieve that always. So the answer to the problem is just minimum of this value over all vertices, and to calculate it, we will calculate the number of leaves in total, and then for every vertex we will like try to take it. Now we need to subtract the number of, like from the all leaves we need to subtract the number of leaves that are directly connected to V, and V itself if it's a leaf. That can be optimal on leaf, like n is equal to 2. But I need to be careful for like n equal to 2 to have a correct answer, which is 0. Um, yeah, I can just iterate over all the neighbors, check how many of them are leaves, and subtract it from that number and update the answer. Um, that just works in linear time. Okay, so I need to count the number of leaves. Now for every vertex as the central one, I'm starting with all leaves. If it is a leaf itself, and decrease it by 1, and also iterate over all the neighbors, and if they are leaves, for each one also decrease curve by 1 and update the answer. Problem E, adjacent XOR. You are given an array of lengths n for each index I such that it is not the last one. You can perform the following operation at most once. Assign AI to be equal to AI XOR AI plus 1. You can choose indices and perform the operations in any sequential order. Given another array B of length n, determine if it is possible to transform A to B. Okay, so we want to transform to a given array. The only way to change some element is to do the operation in that index, and we can do it only once. So after we do the operation in that position, it must be correct. It must be like what we want, number B. Also, it means that like the only numbers that can be on position I is either AI that it was on in the start or BI that it must be in the end. Since we can change it only once, like in the end it must be BI. So before the operation in that index it will be AI. After the operation it must be BI. XOR is a nice operation because like if I know my initial value and what I wanted to become, I know what I should XOR with. And like it is uniquely defined and it's just a XOR of starting value and the result. So for every position, I know what should be the value of the next element at the moment when I apply the operation. Also for the next element, I know that its value is either AI or BI, where I is that position. So if for some position I cannot get the value I should XOR with in the next position, it's just impossible. Otherwise, it's only the question of like whether I should do this operation after the operation on my right neighbor or before that. And I can decide, like I can look at all my conditions, like which operation I should do before which, and we can see that like this is a directed graph that absolutely cannot have cycles because even if we ignore directions, it is just like a bamboo straight line. Um, so it cannot have cycles, therefore it does have a topological ordering. So there is a correct way of ordering those operations. Yeah, there is also a case when AI is the same as BI. That just means that the only operation I could do is XOR 0, but that doesn't do anything, so I just will not do the operation in this index. But also, like, for its left neighbor, like, this position can only be one value because AI and BI are the same. So it wouldn't matter, like, well, I'm just not doing the operation in this position, so like there won't be a condition like should I do the operation in the previous position before or after, because like this operation just not happening. And like both AI and BI are either good or bad for that position, so because they're the same. So actually, like the code is super simple. I just need for every position, like for the last position, I cannot do anything, so they must be the same. For every other position, I need to check that either AI and BI are already equal, or I can use like either AI plus one or BI plus one to XOR with AI, and I must get a BI. If that is not true, then it is impossible. If it is true for every position, then it's actually possible. But like actually printing the order of operations would be like a bit of a harder problem. Um, but since I don't need to do that, it's just like uh, one for basically after reading the input. That's a nice problem. I like it. So for every position except the last one, the good situations are when AI is already BI, or AI XOR AI plus 1 is BI, or AI XOR BI plus 1 is BI. So if that happens, it is good. Otherwise, it's impossible, just return false. That's it. Problem F, unjust binary life. Yuri is given two binary strings A and B, both of which are of length n. What is it? The third or the fourth problem where we are given two arrays of the same length. The two strings dynamically define an n by n grid. Let ij denote the cell in the ith row and j's column. The initial value of cell ij has the value of ai XOR bj. Okay. Yuri's journey always starts at cell 1, 1. From a cell ij, she can only move down to I plus 1 j or right to ij plus 1. A journey is possible if there exists a valid path such that all cells on the path, including 1, 1, have a value of 0. Before her departure, she can do the following operation for any number of times. Choose one index I and flip the value of either AI or BI. The grid will also change accordingly. Let fxy denote the minimum required operation so that Yuri can make her journey to the cell xy. You must determine the sum of xy over fxy over all xy from 1 to n. Okay, this seems pretty easy because well, I think the only way the journey is possible if like all the elements like before xy are zeros, or okay, not okay. They might be all zeros or all ones. Basically, so because let's say that we want to go to an n. In the starting cell, we must have a 0, so A1 and B1 must be the same, so that their XOR is 0. Then we will, so let's say they are zeros for simplicity for now. Then we will move either like I will increase by 1 or j will increase by 1. We need to arrive in the cell where the value is also 0. But like one of the values we XORed stayed the same. And the other one we changed. So those two must be the same. But then like it must be the same as like everything we have seen before. So we will traverse like all the i's up to like all the rows and all the columns. So all the values we have seen must be the same. So fxy is calculated as like what is the minimum number of iterations to make all the values up to like in the array a up to x and in the array b up to y, we must make them the same. So if s is the number of ones, then it's just minimum of s and like x plus y minus s. But now we need to calculate it, like calculate the sum over all x, y. This is actually not that simple. So okay, we can say that fxy is minimum of f0 xy and f1 xy. Like what is the cost to make all the elements to be 0? What is the cost to make all the elements to be 1? Then, like, for example, f0 xy is just the number of ones that we need to make into zeros, and we can write it as a sum of two functions. Like one of the functions only depends on x and the other only depends on y, because like, we just take like some elements in array A and some elements in array B. So we can say that it's like g0 of x plus h0 of y, and the same with f1. Okay, now we can calculate g0, g1, h0, h1 for all x and y in just linear time. So the idea here is well, basically we do not need to process x and y like in order from 1 to n. We just basically we have those functions, and for all x and all of y we need to find the sum of minimums of like those sums. So we will sort them in a different order. Basically, like choosing whether we go with zeros or ones, like on what criteria like do we make the choice? Well, what is cheaper? But how do we define like what's cheaper? Well, we can look at what's cheaper for x, and like the value of how much it is cheaper is like g0 of x minus g1 of x. Like if this is negative, then it is better to go with zeros, and the absolute value will take like will say us how much it is it better. And actually so we can look at this for x's and this for y's, and like we should go with zeros if the sum of those values is negative or like non-positive. Otherwise we will go with ones. So the way we will do it is we will calculate those values for every x and then sort x's by those values, and we can draw it again as a like two-dimensional thing, but like this is like x's sorted by g0 minus g1, and these are y sorted by h0 minus h1. And well, if we are close to this corner, then like it's better to go with zeros, right? Like this is small, like probably smaller than zero, and this is smaller than zero. But when we move in this direction, like it becomes better and better to go with ones, and like at some point it becomes like just better to go with ones. And so actually like there will be like some kind of divide, something like this. So here we will take ones, and here we will take zeros. And we can find like this the shape of this divide um, with like 2 pointers or something, or you can like you can make it simpler by just fixing x, and like for fixed x you find this point with like binary search on sorted array of y's, and then like here we need to take g0 of x plus h0 of y, and here we need to take g1 of x plus h1 of y. Like g0 and g1 are just numbers because like we have fixed x, so we need to multiply them by the length of those things, but to take like sums of h1 and h0, we need to like pre-calculate prefix sums or something. So yeah, you can do that with binary search, or you can do basically the same thing if you sort both of them and do 2 pointers. For me, it is easier with 2 pointers, but that's like personal preference basically. So yeah, like that part is actually not very easy, and like the idea of sorting by difference is well, it's a standard thing, but I'm assuming that it's not very easy to um, come up with like on yourself. Um, so first we will fill in basically the functions g and h, but I will well, I will calculate them, but I will store the difference and one of the functions in arrays A and B, respectively. Since it's all symmetrical, it doesn't really matter. Like, I shouldn't care about like what is 0 and what is 1. Just like if I'm consistent with it, it will be fine. So I'm storing x minus y and y. So to get x, I need to take sum of those. And I'm storing it like this because I need to sort by the difference. So now I will pre-calculate prefix sums for x and for y for both a and b. So I have 4 arrays of prefix sums. Okay, now 2 pointers. If this is like if the sum of firsts is negative, then I'm taking a0 and b0. Otherwise, I'm taking a1, b1. And I should start like one of the pointers is 0 and the other one is n. Well, I guess I will still like have it like non-symmetrical by coordinates because like I need to calculate the sums, and like it is easier if I like kind of iterate on one coordinate and then in the column calculate the sum. So like the sum calculation will be basically the same as like I described for binary search solution. Well, basically 2 pointers is just finding all the like binary search answers but in linear time for all together instead of doing binary search for everyone. So I probably didn't need like some of the prefix sums, but whatever. So I will be decreasing p, and I will be decreasing it while the sum is positive. So first plus bp minus 1 first is greater than 0 minus 1. So in p and after that I want to take 1, like function that takes 1 once, and before that I'm taking zeros. So for the part before I need to add to answer p multiplied by the value that corresponds to the zeros in A, and also ref b0 of p, and for the part after it's like this. Well, that is interesting. It will be cool if like just everything is wrong. But, well, I hope not. I think it should be good. I forgot to calculate prefix sums correctly. Okay. Poke myself in the eye. That's not nice. Problem G. Waffen. To help improve her math, Kudryavka is given a set S that consists of n distinct positive integers. Initially her score is 1. She can perform an arbitrary number of the following operations on the set if it is not empty. Let the minimum value of S be m. Multiply the score by m, remove m from S for every integer I such that I is strictly smaller than m, add I to the set S. It can be shown that no duplicates are added during this step. Sure. She is addicted to performing operations, but after k operations she realizes she forgot her score. Please help her determine her score modulo something. That sounds pretty cool. Okay, so like this thing sounds to me like operation with binary numbers. Like if we look at the binary number, like take the minimum position of 1, then like remove it but insert all the ones before that. That's doing -1 in binary. So basically we're starting with like some number given in binary. We're just given like the positions of 1 bits in it, and then we will like, subtract 1 from it and also multiply the result by the position of the lowest 1 bit. But maybe that interpretation is not even very useful here. We probably just want to note that when we do some operation with some number, we remove that one, insert some smaller ones, and then we will do operations on that newly inserted elements until we exhaust all of them. So basically we can and after we exhaust them, the only change to our set is we removed the smallest element. So basically we can for every element we can try to calculate how it what is the total effect of all the operations this element creates. How many operations there will be? We need that because we know that we need to process exactly k operations, and also what is the product of everything by which we multiplied the score. And the interpretation with binary number helps us to see that the number of operations will always be 2 to the power of that position, I guess, -1. Well, just because we number positions not from 0 but from 1. But the product is not easy to calculate without a dynamic programming. But the thing is, we don't need a lot because one operation with a number 31 already gives 2 to the 30th power of number of operations. So we just need to calculate this dynamic programming up to 31, but then we can evaluate everything quickly enough. We can just do log square. The number of tests is not that big. I think logarithm should be possible, but for simplicity we will just do log square. Okay, so the idea of what is dpk is if we do operation with number k and then do all the operations it created and recursively, the number of operations will be 2 to the power of k minus 1. But what is the product of all the numbers? That's what we want to calculate. How do we calculate that? Well, dp of 1 is 1. Then for every k, we start with operation k. So start with product k. But then we create all smaller numbers. But for them, we already know what is their total effect. So we just multiply all of those numbers. well, here we clearly could do linear, just like maintain the product, then multiply by the new value. Wouldn't be hard, but for the test, like, it is still like somewhat tricky. Okay, so I will be reading my numbers. The numbers that are smaller than k, I will just store that I have them. But among all other numbers, I only need the minimum one, because if we get to that part with bigger numbers, like once I do one operation on that, we create all the numbers that are smaller, and then we won't be able to leave that. Like the number 31 already does more operations than we have. So this is just infinity. And I need to clear if x is small, then we just mark that we have it. Otherwise, we update min big. Okay, now we'll just do the operations in the most straightforward way we can. But we will like skip blocks that are generated by that one number. So basically, like while m is greater than 0, so we still have some operations to do. It is guaranteed that we will not run out of operations, right? It is guaranteed that the set S is not empty before each of the key operations is performed. Great. So while m is 0, we want to find the smallest number we have. So if p is equal to k, it means that we have cleaned the small numbers and we need to use the big one. Sort big it's not inf. Multiply by that number, because that's how the operation is going. And now we are creating all the operations with smaller numbers, but we will only do it for the numbers up to 32. And we have spent one operation, so great, we have spent it. Otherwise, p is smaller than k, we have this operation, and we do it. Something Well, I guess something is wrong with my tabulation. No, I don't like it. That's right. So now, like, I want to do the operations with number p, and ideally I would like to just use my pre-calculated dp value and like do all the operations at once. But that might not be possible because like that's too many operations. So let's see if like that's the number of operations I have. If it is not greater than m, then cool, I can decrease m by that number and do all of them at once. Just set that number to 0 and multiply the answer by dp of p. Otherwise, I cannot do that because like I will stop somewhere in like inside like resolving all those recursive operations that will be created. So I will just do it by hand. I will do one operation and create all smaller, and then we will like continue with our while cycle. And I have spent one operation. Okay, I want to state that this works in not infinite time. I wanted it to be log square, but I don't think it is. Might be log cube. Okay, let's see. We have this while true that like can be long, right? So this can happen only once. We can only one time we can use some big number. So this is just one iteration, doesn't matter. Like we're doing some k here. Okay, so this in total works in O of k. Great. Now this thing is fast, like this whole thing is constant time, but it can be executed several times, right? But every time we do it, we set one element of array A to 0 when it was 1. So I guess we want to use the sum of elements in array A as our potential function. So we have sum in array A and the number of operations we're doing. So here we will reduce sum in the array A by 1 and then like do some constant number of operations. So like the sum of those is constant here. Here it's worse because like again we spend some like linear time, linear of p time to do it, and we also increased the sum, which seems bad. But I state that this happens only once for every p, at most once. Why is that? Well, because when we do it, we know that m is smaller than this, and when we do it, we will set all the smaller to 1, so we will not reach this place again. Um, so, like, once for every p, we can increase the sum by k, so the total increases sum will be at most k square, and so this whole thing works in k square, and k is log of uh, 10 to the 9th power. So yeah, it is log squared. I was correct in my estimation. Probably should run on samples. um, Looks good. Okay, I have reached the last problem and I have 47 minutes still. That might be good, might be a win for me. Problem H, C, U, and coprime. Yumi is given an array A of length n whose elements are integers between 1 and m. She loves coprime integers and wants to find 4 distinct indices PQRS, such as GCD of AP and AQ is 1 and GCD of AR and AS is also 1. If there are multiple solutions, you can output any one of them. So we need to find two non-intersecting pairs of different by position indices such that both pairs are coprime. Interesting. M is up to 10 to the 6 and the sum of M is up to a million. Interesting. How do I find one such pair of coprime elements? I don't know. If I can find one pair, then the problem is probably solved. Because, okay, let's find that pair, then let's remove those two elements and try to find another pair. If we did, great. We have found like two pairs with non-intersecting elements. If we didn't, uh, the only way the solution can exist still if those two numbers we have chosen for the first pair are actually in two different pairs. Like one pair is one of those numbers and something else, and the other pair is the other of those numbers and something else. Why is that? Well, because otherwise, if the solution exists, there will exist a solution uh, like the one we tried to find before. There will be a pair that doesn't use those two elements. Um, and now I can just iterate over all the remaining elements and see like which one of them are k-prime with like one or the other of the two I found before. And then like if well, basically I will find like all the options. If for one of them there is no options, then the answer doesn't exist. If for both there is only one option and it's the same option, then it also doesn't exist. Otherwise, I can choose any option for the one that has less options, and then the other one will still have an option that I didn't ban. Um, so yeah, if I can find one pair, I'm good. And I think I can. That would be weird if that's the simplest way to do it. I have some way, but it's pretty hardcore. But like it does use that M is small, so it might be what they want. Okay, I guess I'll just do that. So when two numbers are co-prime, well, when they do not have a common prime divisor. So our amazing way to find a pair of k-prime numbers will be the following. So we have an array of numbers. We will just iterate over the first number. There is a simple like quadratic way, like n square log, I guess, because we need to calculate GCD to check if the numbers are actually k-prime. Let's just check all the pairs and check with GCD, like check if GCD is 1. That's obviously slow. But we can try to optimize it in the following way. We will try to iterate over the pairs, like let's fix the first element in the pair. And now we have like this suffix where we can try to find the second one. What if I can quickly check if there is one? If I can, then it would be okay to just check all of them and find the correct one, because like I will just stop the search after it. So if I can quickly understand whether there is a co-prime pair to this element on the suffix, I'm good. Or even if I like quickly understand that for the whole array, but it doesn't really matter. Like both things will be the same. So to do that, we will actually count the number of k-prime elements on the suffix, like with this element. If it's 0, then well, it doesn't make sense to run through them to find one because there isn't one. And if there is not non-zero, then we will find one by checking all of them. How do we count the number of k-prime elements? So yeah, instead of checking if there is one, we will count. Sounds harder, right? Well, it turns out that it's actually, well, it's not easier because checking if there is one is like strictly not harder than counting, and that's basically what we're using. But it turns out that because we are counting, we can do some shenanigans like that will allow us to add and subtract, and then we will count correctly. Basically, we will be doing inclusion exclusion. And the idea is that, like, let's say that our number is x. For x, we can find like the primes that it is divisible by. It's actually like it's a product of primes in some powers, but we don't care about the powers. And actually, for for ease of implementation and for like better speed, we will start by like reducing all the numbers to like just a product of all the different primes they have, because in for being k-prime, it's the only thing that matters. The set of primes you have, the powers do not matter. That actually have like some name, the function, but I cannot remember it right now. Radical or something, I think. Like radical of a number x is the product of primes that divide that number, I think. Maybe not radical. But there is surely some name and a 3-letter abbreviation that is used like as a function name. I think it's radical. Okay, so we don't care about the powers. we have some primes. So, and the number of those primes is not very big. Times 3 times 5 times 7 is like 110. If multiplied by 11, it will be this. Multiply by 13 and then by 17. This actually should be something good, right? Like this is 1001 very famously. So this product is the product of this 3, which is 30 like repeated twice, multiplied by 17 is 510,510. So if we multiply by yet another prime, it will become greater than million, so our numbers cannot have that many different prime numbers, so the maximum number of prime divisors a number up to a million can have is like 7. And that also has a name. I think it's like small omega, the number of prime divisors. And big omega is the sum of powers, I think. Okay, so we have those primes. How do we count the k-prime numbers? Let's say they're stored in some set and we know some information about them. Pre-calculate something. So we can start by saying that, well, all the numbers are k-prime except the ones who are divisible by like p1 or p2 or pk and so on. So the number of k-prime numbers is the number of ones that are divisible by 1, which is all of them, minus those that are divisible by p1, minus those that are divisible by p2, and so on, and those that are divisible by pk. But here, like, for example, we subtracted twice the numbers that are divisible by p1 and by p2. So we need to add them back. So the number of numbers that are divisible by p1 and p2 at the same time. But that's just being divisible by the product of p1 and p2. And well, you can see like the inclusion exclusion here. And we just basically, for every prime, there is like a subset that is subset of elements that are divisible by that prime. And we're interested in the like numbers that are outside of those like at most 7 sets that are divisible by the primes that we do have, and counting that thing is inclusion exclusion. So we want to calculate the sum of like this a I used is like the number of elements that are divisible by something. So basically it will be like the sum over all divisors of x minus 1 in the power of like omega of this divisor times the number of elements that are divisible by this. This thing is called mu function of d. For if d does not have like square, like it's not divisible by any square of a prime, and it is the case if x is not like that. But actually, if x is not like that, like this definition with mu would still be correct, and like basically this mu function is created because it's so useful for inclusion exclusion on like number theory problems. So we actually want to calculate this, and how would we do that? Well, numbers like the function a we will just store. For every number we will just calculate how many elements are divisible, and when we will like go left, we will remove the elements from the suffix we're checking, and the removing is done by well, let's take our element, let's go through all the through all its divisors and subtract one from the needed positions of A. And calculating this sum is also like, let's run through all the divisors and take this value that is calculated, take mu, we will also calculate it for simplicity, I guess, and like calculate the sum. Now, if the sum is 0, then we don't have any coprime elements on the suffix. If it is non-zero, then we have, and we can find one by just running to the right and checking every one of them. So that's how we will find coprime pair if it exists. The complexity is like for every element we need to run through its divisors, so you can say that it's like n times the number of divisors, but it's actually like if we only care about the numbers that like have different primes, then the number of divisors is reduced. Like to have a lot of divisors, you need to have like 2 in the big power, 3 in the big power, and so on. So by only considering numbers like this, the number of divisors is actually like a bit smaller. Not by a lot. Like here we are saying it's like 2 to the 7th power, which is 128, and the actual maximum number of divisors is 200. But like it's easier to give like a good bound for that. So our good bound is 2 to the power of like omega of that like maximum omega, which is 7 as we calculated. So this is the number of operations needed to calculate the sum and to maintain the function A. Also, one time when the number of divisors is not number of coprime elements is not 0, we will need to run through all the elements and check for being coprime, which is like another n log so, or m. And now we can like after learning how to find one pair, like finding 2 pairs, I already described, and it's not much harder, but just a lot of busy work. Okay, and I need to implement that in 24 minutes to actually solve the problem on contest. Well, it's not very hard to do, but still, with the explanations, I might need to go a bit fast. Yeah, it's easier to just store all the divisors for all the numbers. I only need divisors that are square free, which should make their number to be like small enough for this to be fast. Okay, so how do we calculate mu? Well, actually, the simplest way that I know is like another inclusion exclusion. I will not explain it right now. That's it. That's a mu function. So now mu function is 0 when the number is not square free, so it's divisible by some square over prime. And otherwise it's -1 to the power of number of prime divisors. So now I will iterate over all the numbers that are square free, and for all the numbers that are divisible by that number, I will say that it's divisible. So in the list of divisors for that number, I will star I. So now every number has a list of square free divisors, and that's what we actually need. Multitask, right? And they need to be a bit careful. Well, actually, no. Actually, I don't need the fact that sum of m is up to 1,000,000. And I guess like I can just write a solution that doesn't use that. It's not that much harder. So I do need that my numbers are not very big, like up to 1,000,000, because I need to create those arrays. But updating them is actually like fast per element. So if I will clear it like not in linear time, it's fine. Okay, let's create array bed where I will mark the elements that I cannot use, because like I want to find a pair, then like ban them, and then try to find another pair. So I will mark them as bad, and like in the function I will just ignore the elements that are bad. Okay, so we'll call find k-prime pair. If I didn't, I will return -1, -1, and if I didn't find even 1, then surely I cannot find 2. If no exists, I'll put 0. Yes, sir. Here's your 0. Then I'm doing return, and that's it. Find k-prime pair will clean after itself. So the array A is filled with zeros initially, and after every call to find k-prime pair, I will make sure that it is filled with zeros again. And I will make it in time like proportional to the size of the array times like 2 to the power of 7, not in linear of m time, although like we are allowed in the problem. Okay, now let's say I found a pair, then I will mark them as bad. Try to find another prime pair. If I did, then I'm good. I can just print those 4 integers. BQ, okay. And that's it. If I didn't, then the only way there is a solution if one pair will use V and the other pair will use U. If not bad, it means that it's not V and U because I cannot reuse elements. And now I'm just checking if GCD of AI and AV is 1, then it is an option for V. And the same for U. Now if opt V is empty or opt U is empty, then it is impossible. So now I made sure that V has at least as many options as U. So for U I can take any option. And for V, I should just take any option that is not the same as the one chosen for U. But if there are no such options, it means that both sizes were 1. And their one option is the same, so there is no answer. Otherwise, I have found my answer. It's V plus 1, opt V at pos plus 1, U plus 1. Okay, and now what's left is to write the function find prime pair. It will fill the array A and then go left to right and empty it like slowly and at any point it will be like it will store correct information for the suffix that is left, and we will be able to count the number of k'prime elements on the suffix with the given one. And if it is non-zero, then we can find one by just checking all of them. And I need to not forget to ignore the bad elements. If not bad, run through all the divisors and increment. Not bad. Run through all the divisors, decrement, and then add to val mu of d multiplied by a of d. If val is 0, continue. Otherwise, we have found the element with non-zero k'prime elements on the suffix. So we will just run through them and find the first one that is good. But first we need to clear A by like removing all the elements that are left. If J was not bad, A of D measurements. If GCD of AI and AJ is 1 and not bad of J, I like that system, like when I mark elements as bad, but I need to not forget to actually ignore them like every time I want to use them in the function. If GCD is 1, then they are coprime, and I can just return that pair. If I haven't found one, something went terribly wrong. And if I haven't found one at all, then I'm just returning -1, -1. Interesting. If it is not -1. So zeros are in the correct positions, and I guess I need to check that 4 and 15 are k'primes, 7 and 9 are k'prime, or 6 and 11 are k'prime, and those two are obviously k'prime. First and fourth 30, yeah, so that is 2, 3, 5, and that is 7, 11, 13, and 2, 3 is well, I'm not checking that. Just 62. But boom. So the contest is more solid than the interesting. Is the one I like to read. bullshit. That's okay. Problem C. Fine, I guess. D is not solved a lot. I thought like kind of the opposite. Like it's very guessable. Like it's very easy to get like how to do something and then just believe that it's optimal. Like I did prove, but the proof was like harder than just guessing. So I would think that D would be very solvable. Like more than it deserves to, because the proof of the solution is not that easy. And E is very nice. I like E, and it is solved a lot. Still don't have accepted. Interesting. I don't think this one is guessable though. Like I mean, there's not a lot to check, but I don't know. It doesn't seem like very guessable to me. Uh, F is not easy already. 1050 and 500. Not bad. G. G is a nice problem. H is well, just asking for one pair would be better, I think, because just two is not that much harder, but that much more annoying to do. Um, just asking for one pair, like it's kind of surprising that like counting is not harder than checking, and that just uh, finding one pair requires almost like trying all of them, but to not try actually all of them, to skip the ones that will not be successful surely. Like you need to do this counting with inclusion exclusion. It is unexpected. Maybe you don't need it. Maybe there is a simpler solution. It's not even very fast. Exactly half of time limit. What's so slow? Probably just putting divisors and vectors, to be honest. Uh, but yeah, it shouldn't be that slow. I don't think so. I mean, I can obviously make it 2 times faster. Like I don't need to like call the function, clear everything, and then call it again. I could have just like when I found one pair, just like remove it and remove the second element of the pair, but then continue going. It will be like 2 times faster. Okay. Yay, I managed to solve all the problems. Let's check it. Yay, all green. Buy a whisker. Like just 5 minutes left. I mean, I submitted like there's 9 minutes left of the clock. Um, Either I'm getting too slow or the contest the contests are too hard these days. Thanks for watching. Bye.